Hello, today we are going to identify ionic and covalent compounds based on the types of elements in their chemical formulas. So some of the compounds we've seen so far in our last unit were ionic compounds. We know ionic compounds require an electrostatic attraction or an ionic bond. And when that occurs, we know electrons are being transferred from the valence shell of the positive ion, your cation, to the negative ion, your anion. When we're looking at things in this next unit coming up, we're looking at things held together by covalent bonds. Covalent bonds require the sharing of electrons. Typically, they're called covalent or molecular compounds. In class, there will be a video that we watch that covers this, but in lieu of that, I'm going to jump straight into the notes. As a reminder, you've probably seen the shell model before, shell or the Bohr model, where we have rings around the atom and we show the valence electrons. I just want to talk about this picture for a minute before we go into the notes. Both of these are equivalent ways to show the sharing of electrons between two atoms. The blue electron was the original valence electron of hydrogen, and this yellow electron was the original electron of oxygen. And when they are showing the overlapping of the circles or the touching of the circles, the rings, that just means that the bonds are being shared, or the electrons are being shared within the bond, sorry. So here's a nice little demonstration between Emily and Sarah. With scenario A, Emily is giving the blanket to Sarah because Sarah is cold, but if they're both cold, they have to share. So example A is definitely a good ionic scenario, whereas scenario B is a covalent scenario. So a molecular or a covalent compound is a group of atoms joined together by covalent bonds. Now, we have seen these already in the last unit when we were doing ionic compounds and writing the formulas for them. Typically, it was things that had metals and nonmetals in them. But when we got to the polyatomic ions, we saw that polyatomic ions were essentially just covalent compounds that had covalent bonds, but the overall molecule had a charge, so it can participate in that electrostatic attraction. A covalent bond forms when the atoms share their valence electrons in order to have a full energy level or a valence shell. And we know we do that so that we can satisfy our octet rule. Typically, molecular compounds have two or more nonmetals. There are a couple of unique cases with polyatomic ions where the polyatomic ions will have a metal and a nonmetal, but they are bonded covalently. You'll see that things like chromate or dichromate are polyatomic ions that form complexes with nonmetal atoms, and the whole thing would end up having a charge. But for the most part, the polyatomic ions we see are made of two or more nonmetals. When we talk about molecular compounds, these things also have two or more nonmetals in their formula. So just a quick recap for our practice. We know that ionic compounds are composed of at least one metal and one nonmetal, but there's a star there, an asterisk, and that's referring to your polyatomic ion. These are things that have at least 3 atoms. One is usually a metal, and the rest are nonmetals. Again, there are some examples like CrO4, 2- chromate, where that chromate is a metal ion, but for the most part, those polyatomic ions do exist as covalent compounds. Now, if you're classifying something as or if you're classifying something with a polyatomic ion, but it also has a metal, it's better to just classify the whole thing as ionic. So if I had something like NaNO3, so sodium nitrate. I know with sodium nitrate, this portion here, the polyatomic ion, has nonmetal atoms in it, but because there are electrostatic attractions occurring, this whole thing I would still classify as an ionic compound. When we're talking about molecular compounds, again, that's two or more nonmetals, so something like CO2 or water. Those things are both molecular or covalent compounds.